Okay. Thank you very much, and I would of course like to thank the organizers both for the invitation to come and speak, as well as for putting so much effort into organizing this conference. It's very nice to be back in person, back from 2D and 3D, three spatial dimensions, and seeing a lot of familiar faces. So today I'm going to talk about some aspects of four-dimensional F-theory flux compactifications. And before I get started, I should mention that what I'll talk about today is primarily based upon work in progress with my collaborators, Monkey Kim and Washington Taylor, both of whom are at MIT, and is also based in some regards, in some respects, on these two other papers that I'll talk about in more detail. So to get started, let me give a few words of motivation. The broad motivation of what I'll talk about today is understanding, or maybe I should more accurately say characterizing the landscape of 4D F-theory flux vacua. So broadly speaking, 4D n=1 F-theory flux vacua are defined by a choice of singular elliptic Calabi-Yau background and p-form flux profiles along the internal space, very roughly speaking. And what's important about these fluxes in these sorts of setups is that they can be used to dial two features, so to speak, of the more realistic looking 4D vacua, namely the massless chiral spectrum and also the presence of a non-trivial superpotential, which in principle can be used to stabilize some of the complex structure moduli. So it's very important to understand these vacua to be able to have complete control over the space of fluxes that we can switch on and include in our setups. And this space of fluxes is best understood in terms of, unfortunately, in terms of the cohomology or homology of resolved elliptic Calabi-Yau, not necessarily the singular ones that we start with. And why is this unfortunate? Well, it's unfortunate because resolutions are rather cumbersome to compute, even though they can be computed, especially for Calabi-Yau fourfolds with a lot of Kodaira singularities, which it turns out is rather generic in the F-theory landscape. So the motivating question here is, can we simplify this problem somehow and avoid the complications that are introduced when having to deal with these singularities? So here's a bit of philosophy. As you all very well know, I'm sure F-theory, again, is defined by singular elliptic Calabi-Yau, and the resolutions or deformations that we typically study in these setups are, I think, best viewed as an indirect method to probe the physics of the singular limit. And in principle, ideally, one would like a more direct formulation of F-theory directly at the singular, in terms of a singular type 2B or F-theoretic background, including, or you can view this as type 2B with 7 branes. And unfortunately, a direct formulation, while being anticipated, isn't fully understood, although there's some very interesting progress that's been made, and I should maybe draw your attention to a paper that just came out a couple of days ago on the archive. So short of a fully completely direct formulation of F-theory, the next best thing that one could hope for is at least a resolution invariant characterization of the physics of an F-theory background. And to give a few examples that are very well known, one thing we understand is that the gauge algebra associated to an F-theory background is can be understood geometrically in terms of singular fiber types in codimension 1 over codimension 1 loci of the F-theory base. So these are classified by Kodaira fibers plus the addition of some tape monodromy to bring this into contact with non-simply laced groups. You could also talk about 6D local matter, which is associated to codimension 2 fibers over so-called matter curves in the base. And then there's the possibility of looking at things like anomalies, which are encoded in the characteristic features of the geometric background. And here I've just, I apologize that it's a bit small, but I've shamelessly copied a couple of tables from 2 different papers just to illustrate these ideas more clearly. So here you see a classification of a list of the Kodaira fibers, and this is a sort of a geometric picture of what they look like once they're resolved. And in this table, we have a list of the matter curves, so-called matter curves that, matter loci that appear in codimension 2, over which the fibers further degenerate, signaling the presence of a local charge matter under the gauge algebra. So this, in the spirit of this philosophy, one might like to ask if we can do a similar thing for 4D F-theory vacua, and in particular, can we do this for fluxes? Is there some way to understand them directly in terms of geometry in a way that's independent of having to deal with the headache of resolving these spaces. So what I'm going to talk about today is hopefully headed towards a resolution-varying characterization. And in particular, what I'll do is I'll sketch some broad features of a proposal for characterizing 4D F-theory flux vacua in the large volume / large complex structure limit in a potentially resolution-invariant manner. And this is going to involve three major ingredients. So the first ingredient is what I'll call local intersection theory for resolutions of singular elliptic Claviau. The second ingredient is a conjecture, namely that the vertical intersection pairing is a resolution invariant, so it's really a datum, if you like, of the F-theory vacuum in the singular limit. And the third ingredient is going to be something called factorized mirror symmetry, and I'll explain in more detail what each of these three things actually corresponds to later in the talk. And finally, after introducing these ingredients and using them to sort of sketch this broad proposal, I'll illustrate the program with a simple example, which is work in progress, and that's a very basic example, actually, in 4D F-theory backgrounds. It's just a smooth elliptic vibration over the base P3. Okay, so here is the plan for my talk. I'll first set the stage and say in a little bit more detail what I mean by 4D F-theory flux vacua, and I'll review some broad features that are relevant to the later discussion. I'll then move on to talk about four-form fluxes in M-theory, which will provide a dual description of the F-theory background compactified on a circle. Then I'll move on to sketch the broad features of this proposal after having introduced the various ingredients that I alluded to on the previous slide. I'll talk about these ingredients in the context of, this proposal really, in the context of the mirror symmetric, the mirror dual of the elliptic vibration over a smooth elliptic vibration over P3. And then finally, I'll conclude and give a few future directions for this program. So before I get started, are there any questions about anything I've said so far? Okay. So let's get started. Let me set the stage. So for me, a 4D F-theory flux vacuum will be a 4D n=1 F-theory compactification on a singular elliptic Claviau fourfold, which I'll denote as X naught. And the setup, as I'm sure many people here are very familiar with, we think of 7 branes as wrapping complex surfaces sitting inside of the base. So here is my very schematic drawing of the base. That's this blue plane that I've drawn. And the surfaces are codimension 1, complex codimension 1 holomorphic objects, geometric objects that sit inside the base. That's symbolized by these red lines that I've drawn. And we'll think of 7 branes wrapping these surfaces. And I'm going to denote each of these surfaces by a sigma sub s. Associated to these 7 branes, to each of them is a gauge bundle, since there is just in general, it's not just a single 7 brane, but could be a stack, so there'll be some, generically speaking, some non-trivial gauge bundle. And then at their intersections, there will be a so-called matter curve, C sub r, and this local matter curve supports local matter, which is signaled by the structure of the singular fibers over the matter curve. And one can recover the chiral index in principle by switching on a magnetic gauge flux along this portion of the internal space. So that's one aspect of the fluxes that corresponds to interesting physical information at low energies. Another aspect is Raman or NS. Sorry, this is not supposed to say NS, but just NS fluxes. These can produce an F-term potential at lower energies. Okay. So this background, as you can see here, it's singular in general. The fiber is away from the 7 brane gauge divisors inside of the base are smooth, but as you move the fibers towards one of these guys, you can see that a singularity develops. It corresponds to, say, a cycle pinching off. That's why I have a sort of a pinch cycle drawn here. And it's difficult to interpret the physics, so what one would like to do is resolve the background in order to understand some aspects of the low energy physics more clearly. And we can do this by compactifying on a circle and switching on some vevs of of vector multiplet scalars, which correspond to the holonomies of the gauge field leg along the compact direction. So this will introduce some adjoint Higgsing. It'll break the gauge group, generically speaking, to U1 to the maximal torus. It's just a product of U1s. And there's a dual description of the setup, which is F theory on X, which is, X is now what I'll use to denote the resolution of the singular background X naught. So this is F theory really on X times S1, and this is dually described by M theory compactified on X. So the broad features we'll need here are that the duality, roughly speaking, maps the F theory Coulomb branch to semi-classical F theory. So there's one loop, quantum corrections that are mapped to the semi-classics of M theory. And in particular, the open/closed string sectors map to bulk fields. So for example, you can expand the M theory 4 form in the vicinity of a 7-brane stack in terms of a collection of 1, 1 forms. These are like a basis for the Kähler form of the smooth Calabi-Yau space, wedged with the field strengths of the abelian gauge fields. These are the Cartan gauge fields in the theory. And importantly for us, the fluxes are fully captured by the G4 profile in the M theory duality frame. Okay, so that's the basic setup. Let me move on to talk about 4-form fluxes in M theory. So let's take a step back and just consider M theory on a smooth Calabi-Yau 4-fold with 4-form flux. It doesn't necessarily have to be elliptic for what I'm saying to be true, but we'll later specialize to the case that the CY4 is elliptic. So really, I'm going to be talking about 11D supergravity on a smooth background. This is the bosonic part of the action that's relevant for the talk. There's obviously some other terms you can add, which are suppressed. And if we want to consider a supersymmetric vacuum with a non-trivial profile for G4, which is the field strength of the M theory 3 form, this has to satisfy various consistency conditions. One of those is quantization, which you can think of as removing the possibility of a fermion anomaly on the M5 brane world volume. There's this funny half-integer quantization, but for this talk today, I'm just going to assume that we picked the geometry so that this guy is even, and then we can just ignore the half-integer quantization. There's also tadpole cancellation. We want the charge on the compact space to be equal to 0, so there's some relationship between the Euler characteristic of the Calabi-Yau space and, sorry, this is supposed to read the integral of G4 wedge G4, and this is the condition that has to be satisfied, and we also want this to be a positive or at least non-negative integer. And finally, if we want to preserve supersymmetry, we have to minimize the so-called Gukov-Alpha-Witten superpotential plus the twisted superpotential. It's the sum of these two objects right here. And most relevant to the discussion today will be the fact that if we minimize this guy, the GVW superpotential, we'll find that the flux is it's forced to be of 2, 2 type. So it sits inside of this intersection of the 2, 2 subgroup of the middle cohomology with the intersection of this with H4. Okay, so how do we characterize the space of fluxes that we can turn on? One way we can think about the space is as a lattice. So we'll think of H4 of the Calabi-Yau as a lattice with a quadratic form, which I denote by Q. And Q can just be thought of as the integral of the wedge product of 2 elements where A and B both belong to H4. So when I say a lattice, I really do mean that it's an integer vector space, but it also is equipped with a particular quadratic form with integer values. And there's also, in addition, we can further refine our description of the space of fluxes by this orthogonal decomposition of the middle cohomology. So it splits into a horizontal part, so-called horizontal part, a vertical part, which is of 2, 2 type, and the remainder part, which I'm not really going to talk about too much today. So for the purposes of my talk today, I'm just going to ignore this, but I will make some further comments on it later on. So in view of the fact that this lattice is equipped with a quadratic form, there's also a decomposition of the lattice pairing Q into a horizontal part, a vertical part, and then a remainder part, which I won't have too much to say about today. So what do the vertical and the horizontal parts correspond to? Well, we can think of the vertical part as H22 sub V as containing all the 4 forms that are Poincare dual to algebraic cycles, and it's generated by wedge products of 1, 1 forms, which provide a basis of the Kähler form J. And importantly, if I pick my flux G4 to sit inside of the vertical part, I'll find that the GVW superpotential is equal to 0. So this vanishes. The horizontal part, by contrast, is it's Poincare dual to special Lagrangian submanifolds. And if I pick flux to be to lie purely along this direction inside of H4, then I'll find that the twisted superpotential vanishes. And another important fact is that these guys are 2,2 type, which is required by supersymmetry only for certain choices of the complex structure moduli. So the vertical pairing on the middle cohomology will be relevant for this twisted superpotential and the physics of the chiral spectrum. And by contrast, if we just think about the horizontal part is relevant for understanding the GVW superpotential. Any questions so far? Okay. So let's first talk about vertical fluxes and their relationship to 4D chiral indices. So I'm going to assume now that my CY4 is not just an elliptic Calabi-Yau, is not just an ordinary or generic Calabi-Yau, but it's elliptic, that's an elliptic fibration structure. And I'll moreover assume that it resolves some singular choice of elliptically fibered Calabi-Yau X naught, which corresponds to the F-theory background. And I'll assume that the singularities that have been chosen correspond to a simple group G. So I'm not going to consider U1s in this talk, but much of what I discussed today can be extended to the case where you have U1s. This group G will be tuned over a gauge divisor sigma sitting inside of the base. Again, that's sort of schematically denoted by this red curve here. I apologize that it's a bit tiny. And in particular, what this means is that the cohomology H11, so in other words, the space of harmonic 1,1 forms, has a particular canonical choice of basis. And I'm going to take G4 to be purely vertical for this part of the talk. So in the F-theory limit, there are some consistency conditions, and namely that there's a D-term potential that's generated, and this, in principle, fixes some of the Kähler moduli. So if I assume unbroken gauge symmetry and that all of these consistency conditions are satisfied, I can compute the chiral index associated to a representation R that's charged under the gauge group G. The chiral index is just the number of chiral multiplets minus the number of antichiral multiplets. And this can be given by an integral of G4 over a so-called matter surface. This is a holomorphic surface. And this can be expressed in terms of the vertical pairing Q sub V. And so I can write this as the vertical pairing of G4 with the Poincare dual of this matter surface for a suitable choice of G4. So as promised, this is the precise sense in which the vertical pairing is relevant to understanding the physics of chiral matter, or the chiral mass, the massless chiral spectrum in 4D. And here I've drawn a schematic picture of this. So if you have two gauge divisors, these two red guys, two red curves that are intersecting in some, so these are surfaces again, recall. They'll intersect generically speaking in a curve. And if I take a component of the resolved elliptic fiber over this curve, if I fiber it over this curve at the intersection, then I get a surface. And this is topologically what you expect the matter surface to look like in some cases. So this computation also recovers the direct or more direct F-theory computation, which was done some time ago, namely where you think about one can view the chiral index as the integral of some characteristic classes over this matter curve. So this is a more of an intrinsic definition in some sense. It doesn't depend on a choice of resolution, but the resolution does, in fact, contain all the information that you'd want, and so you can resolve and equally well compute the chiral index in terms of this G4 integrated over this smooth choice of surface. So if we want to understand the pairing on the vertical subgroup better, what we can do is we can compute the matrix elements of this pairing just by taking wedge products of these 1,1 forms, assuming some choice of integral basis. But I'll be a bit schematic about that for now, and I'll talk about the details of finding an integral basis later on. Okay, so that's vertical fluxes. What about horizontal fluxes in the relationship to the Gukov-Alpha-Witten superpotential? Well, we can write, as I mentioned before, the superpotential is given by this expression. It's the integral of G4 wedge with the holomorphic 4 form of the Calabi-Yau. And this can be expressed in terms of the so-called periods of the Calabi-Yau, which are just given by the integral of the 4 form over some 4 cycles, which are a basis of the horizontal homology subgroup. And again, this entire thing can be written in terms of a pairing. If you like, you can think of this as a lattice pairing. And what this says is that the superpotential itself can be written as a pairing in particular between horizontal G4, if I just think about horizontal, the horizontal part, and the holomorphic 4 form. So there is a difficulty in computing this guy directly. The periods are somewhat subtle to compute in an integral basis. You could recover them as the solutions of a Picard-Fuchs system of partial differential equations. There is an interesting workaround that's been proposed, and that's in many ways going to form the basis of what I talk about today, and that's to use mirror symmetry of type 2a compactifying on a Calabi-Yau fourfold, which identifies the periods of X with B-brane central charges. And if you do this at the large volume or large /large complex structure limit, the central charges are really, you can just view them as the central charges of D-branes wrapping holomorphic cycles. And this leads to an expression for these central charges, at least at leading order, in terms of the volumes of the calibrated volumes of various cycles inside of the Calabi-Yau. So again, this can be written in terms of integrals of wedge products of these 1,1 forms and the mirror symmetry setup. So the upshot of this is that at least at the very at large complex structure points, if I want to understand what the horizontal pairing looks like, this guy, I can express it in terms of the vertical pairing of some mirror Calabi-Yau. I'll talk more about this later on. So this is what this does in effect is it sort of shifts the focus of the talk really just onto understanding the vertical part of the lattice pairing. Okay. So let me give a sketch of the proposal. And the proposal, again, is to find a resolution invariant characterization of this lattice pairing. So as I said, there's 3 ingredients. The first ingredient is what I'll call local intersection theory. Local intersection theory, in this case, in this context, it really means that we can do intersection theory to figure out how to compute. So we want to compute these wedge products of 1,1 forms. And the statement is that they can be viewed as intersection products. In other words, the matrix elements of the vertical pairing can be viewed as intersection products of these divisors, D hat sub I, where the divisors are really just the Poincare duals of the 1,1 forms. So what do I mean by local? Well, as an algebraic variety, if I view the smooth elliptic Calabi-Yau fourfold, which resolves my singular space that defines the F-theory background as an algebraic variety, has a projection down to the base, right? Because it's an elliptic fibration. So the projection it kills off the fiber and it puts you down into the base of the elliptic fibration. And in the language of algebraic geometry, this can be viewed as a morphism. So it turns out that because this has the right properties to be considered what's called a proper morphism, I won't really get into the technical details of this. It turns out that one can compute the push forward of this map. So I'm going to call the map pi. The push forward is pi star, and I can act with this map on any intersection product of these divisors. And the image of the map will be a linear combination of intersection products of divisors sitting inside of the base. So you can think of this, roughly speaking, as going back to this integral right here, and then integrating over the T2 direction. So now that you have an integral of, or a linear combination of integrals of 1,1 forms sitting inside of the base. So the push forward pi star is very easily computed for blowups, right? The things that we use these are sort of the maps that we use, like just going back to a picture that I had earlier. A blowup is really what I'm doing when I I cut out a singular piece of the geometry and I replace it with a smooth space. And so this is sort of these are the building blocks of a resolution. And the nice thing about this push forward technology, if you like, is that it can be very easily computed for resolutions that are decomposable into sequences of blowups along complete intersections of hypersurfaces of Calabi-Yau. And it can be done, it doesn't require a global, sort of a global specification of the Claviau background. It really only requires a local specification, so I can write down some local Weierstrass model, y squared is equal to x cubed plus fx plus g, and take the projective closure of the fibers, but not necessarily, I don't necessarily need to specify the global geometry of the base. So if I have a local singularity realized in this manner, meaning a singularity realized over some local patch of the base, right? So suppose I just look at some local feature here. I have singular fibers sitting over this local region. If I do a resolution of this local space along particular types of complete intersections inside of the Claviau, the local Claviau, then it turns out that this push-forward map can be applied, it can be factored, if you like, into push-forwards. So it can be written as a composition of push-forwards of blowdown maps, if you like. So let's call one of them P. Sorry, need to switch to more permanent. So, right, we can imagine that I lift this map into a composition of push-forward maps that are defined with respect to each of the blowdowns, which contract the exceptional divisor of the blowup. So if I have a collection of, let's say, R of them, then I would start with the rth one and take the push forward of that, and then the r minus 1 guy, and so on and so forth. So this is a very nice expression that's very easy to compute. And it turns out that the action of these push forward maps is understood not only for intersection products of divisors, but it's also understood for any analytic function of these divisors. So I can imagine having a formal power series in them, like you might see with a characteristic class like the Chern polynomial or something like that, or the Chern character. And the push-forward map has a very nice, well-controlled action on analytic functions such as these that have a power series expansion and can be computed very quickly. So why is this useful? It's useful because you can then leverage this nice feature of the push-forward map to compute intersection products very quickly. And indeed, there's some new work that I'd like to take a moment to advertise very quickly that's going to appear in the next couple of days, hopefully, where we define a very simple function, actually. It's really just the exponential of a choice of Kähler class for the Claviau. And we treat this as a generating function because you can just take derivatives of the exponential of this guy with respect to these parameters phi, these Kähler parameters, to pull down any number of products of the divisor classes in order to compute their intersection products. And so we just compute the push forward of this guy and write down some generating function that only depends on the local geometric features of that specify the details of the Claviau singularity. So one of those is the canonical class of the base. This is just the first Chern class, or minus the first Chern class of the base. And then we also have sigma, which is the 7-brane gauge stack where the 7-brane singularity occurs. So let me just give a very quick example of this. You could look at, for example, the resolved SO8 F-theory model. And here I've just presented the final answer. So it's some horrible, complicated looking function, but it's actually despite how nasty it looks, it can be computed very quickly, and all you have to do is take derivatives of this function with respect to the Kähler parameters to pull down any intersection number you like. And the beauty of this is that because it's a local expression in some sense, you don't need to specify the full global geometry of the base, and it works for any choice of base as long as it has these local features specifying the SO8 singularity. So this is nice because it gives a flexibility in being able to look at many different types of Claviau backgrounds for F-theory, and as I said, also the algorithm is very quick. And so here I just, for work on my collaborator's laptop, you can sort of, we have a package that we're going to release and hopefully that people will use, and the package can be used even on a home laptop to compute intersection numbers, to compute this generating function for models with gauge groups of rather large rank and very short amount of time. So this is a big boost as far as I'm aware in the computational power that's available. And in principle, if you had some very nasty F-theory model with lots of different gauge groups, it isn't really a huge obstruction to being able to compute their geometric properties. This is also useful, by the way, for looking at other Computing other features, other characteristic numbers, for example, if you wanted to compute the Euler character, it's actually faster in practice to compute this guy and then just plug the intersection numbers that you extract from the generating function into an expansion of the Euler character. So anyway, that's an aside, but the key feature, the takeaway here, is that there's this sort of local program of intersection theory that one can use. And what this allows us to do in particular is figure out or derive, if you like, a sort of canonical representation for the pairing on middle cohomology, the vertical pairing on middle cohomology. So namely, we pick some basis, and this is a bit of an abusive notation. What I mean by this omega sub ij, this is defined to be the wedge product of omega I with omega j, or if you think about the Poincare dual, it's really the intersection of two divisors, di dot dj. And this is what if we take the full pairing of all of these guys, so the full set of intersection numbers and arrange them into a matrix, right? So I can take any intersection number, di, dj, dk, dl, and I can split it into the ij directions and the kl directions and write down some matrix where these are the indices of the matrix and push the entire thing down onto the base. And I get some canonical expression that looks like this, that depends schematically on some choice of divisors for the base. And these blue characteristic classes or divisors, if you like, which correspond to the singularities or the singularities of these are really the 7 brane stacks inside of the base. So again, I'm using sigma to denote this 7 brane stack over which the elliptic fiber singularity is tuned, and some representation theoretic objects that are denoted here in red. So here, for example, kappa ij is the inverse metric on the Lie algebra. This coincides with the Cartan for simply laced algebras. And then these rho ijk are the coefficients of the so-called prepotential. I can talk more about this if anybody's interested in the details. And finally, in this lower right block, we have some other intersection numbers that I'm just going to denote schematically, and these are related to the chiral indices. So there's some canonical form that I can use for the restriction of the quadratic form in middle cohomology to the vertical part. So here I just wrote down something that applies for a single group. If I have a product of groups, some more complicated setup, again, it fits into this sort of canonical form where you have this sort of global geometric part for the base in the upper left corner. That's this guy right here, this block. You have a bunch of blocks associated with each of the 7 brane stacks. And then you have some part down here in the lower right, which corresponds to contributions from chiral degrees of freedom. And we can think of these as corresponding to the junctions between two 7 brane gauge divisors. So if you have a pair of divisors, sigma s and sigma t, that intersect one another inside of the base, was the case, for example, when I talked about the matter surfaces. Then there's some contribution that is relevant for computing the chiral index, and that sits here. And because it involves really these combinations of 7 brane stacks, these junctions of them, there's going to be some gluing vectors that couple with that couple G1 to G2 or G2 to G3 and so on. So this is the canonical form right here. So you might be thinking, like, why is this special? I could have picked any resolution and maybe found something like this, but these things ought to differ depending on the choice of resolution that I picked. But the key point is that there is a second ingredient which makes this especially useful for us, this canonical form. And the second ingredient is, in fact, a conjecture that the canonical form is not only canonical, but it's also a resolution invariant in the sense that you can find an integer change of basis for any pair of resolutions that will put these two canonical forms into the exact same form, matrix element by matrix element. So let me state that a little bit more clearly. If I picked, and this has been tested, but again, I have to stress it hasn't been proven. If I pick any two resolutions of my singular F-theory background, and I compute their pairings QV, the evidence seems to suggest that there exists a lattice change of basis. So there's some unimodular integer valued matrix that I can use to change basis from one vertical pairing to the other. So why should this be true? Physically, you might expect this to be true because the chiral index is independent of the choice of resolution. It's just something, it's an intrinsic property of the 4D spectrum. It doesn't care which resolution you pick. It really is something that, in some sense, defines the singular F-theory background directly. And this is, again, computed by, it's computed in terms of the product, or the pairing, if you like, between vertical flux and a matter surface. Or really, I should have the Poincare dual right here, so this is a bit of a typo. But it's something that's computed by this object Q sub V. So because this is invariant, you might suspect that maybe there's a possibility for the pairing itself to be invariant. And this is even further supported by the idea that the matter surfaces themselves and the set of fluxes that can be lifted from the M theory background to F theory are really just, they sit inside of a linear subspace. So you could write this as a projection of the flux. It's just some vector, and I'm projecting it onto a subspace. Or I could take the same projector P and act on the pairing itself, and I get a different matrix. And to be consistent with this entire expression, what I should find, and what is indeed supported by computations, is that the rank of the projection of this matrix is equal to the number of independent families of chiral matter that I have in 4D. So that's the physics intuition. There's also a hint from mathematics, namely that the Chern numbers or Pontryagin numbers of fourfolds are birational invariant. So they're not only topological, but they're independent of a choice of resolution. And you can write down the signature as which is really just the number of, so the signature is, you can think of it as the signature of the pairing Q, thought of as a matrix. It's the number of positive, negative, and zero eigenvalues. And that can be expressed as a linear combination of these guys. And so this is also a birational invariant, but this isn't quite enough to prove this conjecture that QV is a resolution invariant. So it's a bit of a hint, but it's not enough to get you all the way there. Anyway, what's important about this is that if it's true, it implies that the canonical form of this pairing can be computed once for all relevant local singularity types, and then you can just be finished and have a sort of expression that applies once and for all for any choice of local singularity structure that defines an F-theory or a local F-theory model. And this can be proven actually in some special cases, but again, not in full generality. I can come back to this point maybe at the end if there's time. So let me move on to the third ingredient, and the third ingredient is something that has been dubbed in the literature in some papers as factorized mirror symmetry. So this is relevant for, what I've told you so far is a way to kind of characterize the middle cohomology pairing, the vertical part, which is relevant for chiral indices in a sort of resolution invariant manner, but I haven't said anything so far about the horizontal part, other than the fact that you could go to large volume / large complex structure limit and potentially use mirror symmetry. So if we want to leverage what I've said just now about the vertical pairing, QV, to be able to compute the horizontal part, there has to be some way to view the mirror elliptic Calabi-Yau in an elliptic or F-theoretic phase. In other words, it has to have the structure of an elliptic fibration such that it can be thought of as a background for F-theory. Yes? Okay. So this is not really an obstruction. It's been demonstrated that most of the known Calabi-Yau threefolds and fourfolds have at least one elliptic fibration structure, sometimes multiple structures. And there is a way to formulate this famous Batirev construction of mirror Calabi-Yau pairs in such a way that one can immediately predict what at least for Calabi-Yau hypersurfaces of toric varieties, one can immediately write down what the corresponding elliptic phase, at least a singular elliptic phase of the mirror Calabi-Yau has to look like. So this is what I mean by factorized mirror symmetry. There's a way to realize the elliptic curve, the elliptic fibration rather, inside of a toric variety such that one can apply the mirror symmetry construction separately in some sense to the fiber and to the base. And this allows us to predict what the mirror F-theory description of the mirror Calabi-Yau. So that involves a choice of base and then some choice of Kodaira singularities corresponding to 7 brane stacks. And once we have this, again, the same technology for the vertical pairing works. So in the remaining 5 or so minutes, let me just sketch out a quick example of this. So this is work in progress. So you could look at mirror symmetry. It has been looked at, rather, in the case of the smooth elliptic fibration over a base, P2. Mirror symmetry just, it swaps these cohomology groups and Hodge numbers. And in the simple case, a simple subset of cases to which this mirror elliptic fibration over P2 belongs, the mirror base, B star, is defined by the condition that the canonical class is equal to -6 of the canonical class of the original base. So those of you who are familiar with toric geometry, you're probably very familiar with the toric polytope for P2. So this is the base on one side, and then the mirror is this horrible looking thing over here. These different colored rays correspond to divisors sitting inside of the base along which different gauge groups are attuned. So you have this E8, a bunch of E8s, F4s, G2 times SU2 singularities. And one can match the Hodge numbers and so on and show that the entire thing hangs together very nicely, and mirror symmetry works as expected for threefolds. Okay, so that's kind of the prototypical example, and now let me talk about the real example, the real work in progress. And that's to think about this, which appears in many ways to be the simplest example one could look at. It's just the mirror or the smooth elliptic fibration over the base P3. Calabi-Yau fourfold mirror symmetry swaps the Hodge numbers as follows. And the toric polytope, which is, this is now a toric threefold. So it looks like some tetrahedron, a simplex with these primitive lattice vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, and -1, -1, -1. So the simplex is the convex hull of these guys inside of the lattice. And the toric polytope for the dual, or for the mirror dual, is some horrible, very large simplex, if you like, with these lattice vectors. So it's the convex hull of this, and you have to, of course, it's very singular, you have to pick some resolution of it, and that's what this picture is meant to illustrate. This is just a face, one of the two-dimensional faces, or the projection of a two-dimensional face, and the different colors correspond to, the points of different color correspond to different gauge factors, like E8s, a bunch of F4s, G2s, and SU2s. The lines correspond to matter charged under the different groups. One can confirm, at the very least, that the Hodge numbers make sense. You can use the Shioda-Tate-Wazier formula to compare the two Hodge numbers on both sides and show that mirror symmetry works as expected. So the goal here is to compute, the vertical pairing, and the result, and as applied to this case, is that you can sort of decompose the pairing into these different sectors. So there's a bunch of E8 sectors, F4 sectors, G2, and SU2. And the exercise, which is work in progress, is to really just to recover the computation of the Hodge number, the vertical Hodge number, the vertical part or contribution to H2, 2, which can be computed using toric geometry methods. So we would like to recover this using this sort of schematic picture, this canonical form. And there's an expression one can write down to make this counting precise. I don't really have time to go into the details of it, but it is consistent with this sort of decomposition of the vertical pairing into these blocks. So finally, just one more comment is that one nice thing about this whole program is that Poincare duality implies that H4 is a unimodular lattice, and this can be used to fix the proper quantization of G4. So one thing I've been a bit schematic, or I've kind of swept under the rug during this talk, is that the precise quantization of the fluxes. And it's a bit hard to find them in particular because an integral basis of the fluxes doesn't necessarily split over the vertical and the horizontal parts, and you may have fractional contributions in both if you really find the actual integral basis for these guys. But for the elliptic fibration over P3, it's a known result that the remainder part of the cohomology, so remember there's this decomposition into H4 horizontal plus H2, 2 vertical plus H2, 2 remainder. And I didn't say much about this guy, but it actually vanishes for this particular elliptic fibration. So this implies that at the large volume / large complex structure limit, it will just be the sum of these two guys, the vertical and the horizontal parts that are unimodular. And we can compute very easily the vertical guy for the smooth elliptic fibration over P3. It's manifestly unimodular, so this implies that the horizontal part has to be unimodular. And moreover, since the E8 blocks in this decomposition are separately unimodular, this implies that there has to be something to restore unimodularity for the remaining part, and that has to be, one can argue, an overlattice that's taken over these other gauge sectors. So this holds a promise of allowing us to, in principle, determine the exact quantized fluxes for the elliptic fibration over P3 at large volume / large complex structure. Okay, so I'm just out of time now. Let me summarize and mention a few future directions. So today I sketched a program or a long-term vision for characterizing 4D F-theory flux vacua in a potentially resolution invariant manner. And it combines various aspects of intersection theory, mirror symmetry, and toric geometry. There's obviously some work left to be done. One of those things is to finish the computation of this sum of vertical and horizontal pairings for the smooth elliptic fibration over, not only over P3, but any combination where these 3 integers add up to 3. So you could take smooth elliptic fibration over P2 times P1 or P1 times P1 times P1. And really, the work left to be done here is just characterizing carefully the different singularity contributions and then fitting them all together in this schematic matrix. There's also the business of having a precise argument for getting this overlattice. There's some hints that this can be done by arguing that there have to be additional charged objects in the spectrum that would correspond to taking surfaces with, let's say, like half integer or fractional coefficients. And then also, like, once this has been done in more complicated cases, one would like to systematize or automate the computation of the mirror base and of these 2 contributions to the pairing. And as far as future directions, I'll just list a few of them here in order of increasing speculation. So you might ask about the remainder part of the pairing, the full unimodular Q for more complicated examples, and this has the possibility to give a method for computing exact quantized fluxes, which is useful for understanding the number of generations in gut models. One might also, from a more mathematical perspective, like to try and prove birational invariance of the pairing of the vertical middle cohomology, and maybe even extend this to invariance over some regions of complex structure moduli space. So this is potentially, in some sense, analogous to the Euler character. And then, thinking a little bit more vaguely and further, more long-term, maybe this offers a more complete characterization, or as a first step towards a more complete characterization of F-theory and the singular limit. So one could start listing resolution invariance. And finally, what would be very, very nice for building or constructing realistic vacua is to determine the horizontal pairing away from the large complex structure limit. So for finite values, like for complex structure moduli. And I will stop here. Thanks very much for your attention. Hi.
Just wondering about the speed up that you guys have on this. So what are you comparing against that plot?
This plot?
Yeah.
But this plot wasn't really you're asking like what does it implicitly compare against? Yeah. It's a compare, I won't claim that this is a speed up, known very carefully compared to all methods that have been used for this computation, but we at least have done some computations on our own. So an example would be like for, using these push-forward methods in the past and using known like algorithms that have been published in the literature for this particular push-forward computation that I'm aware of would have taken maybe, let's say, like half a day on my laptop to compute the E6 numbers, or a full day or something like that. It takes it takes a minute or maybe 2 minutes, or it takes, I think, under a minute to compute E6. If you want to do E6 times E6, it takes under 10 minutes to do something like that. So it seems to be pretty fast. Maybe I can't claim like definitively that it's the fastest, but
Is it done in Mathematica? Or?
yeah, Mathematica, yeah.
I mean, I'm sure you're aware of this, but there's like, you can also implement this kind of computation in like quotient ring formulation, and then there's this singular program. And my experience with that is basically, you can go up to hundreds of variables, and this thing spits it out in seconds.
This is on your personal machine or on a cluster?
Yeah, on my personal machine.
I see. Interesting. Well, yeah, I would like to chat with you about this then. Yeah, maybe we can compare notes then. Thanks.
Okay, my suggestion is, given that the lunch time is already a little bit short time, I would the lunchtime. So let's thank Patrick again.
Thanks.